In this video, we're going to show you how to make pseudo-relative permeability curves with ExcSim. Pseudo-relative permeability curves are a means of incorporating more accurate physics into each grid block. The pseudo curves are determined from the small, detailed cross-section models and then incorporated into larger, coarser aerial models. Some advantages of pseudo curves: they let you represent 3D problems in 2D simulators, heterogeneities in the vertical and horizontal direction, and various forces such as capillary and gravitational forces can be taken into account. Furthermore, they suppress numerical dispersion, which is a non-physical flow of the displacing fluid into neighboring grid blocks. Some disadvantages are that generating pseudocurves can be cumbersome. With ExcSim, it's very easy. I'll show you. And pseudocurves are not well understood by all simulation engineers. And there's a belief that more grid blocks are a simpler option. Pseudos cannot fully solve all grid resolution issues, such as local balance between gravity and viscous forces in well coning and cusping situations. The example we're going to show you here is we're going to upscale a 5-layered oil-water relative permeability model. And the model is shown here. It's a 35 feet long model, 5 layers, and each layer is subdivided into 35 grid blocks of 1 foot width or length. And the total package is about 31 feet thick. Now the idea is to upscale. We're going to run a simulation through this model and then upscale the relative permeability curves that we can then apply to one single coarse grid block in a 2-dimensional model. So here we have the thicknesses of each layer: 5 feet, 10 feet, 3 feet, 5 feet, and 8 feet. And each has different permeability and different porosities. And we also have a transmissibility multiplier of 0.1 in the vertical direction. So when we upscaled the relative permeability curves, such as you take this fine scale curve, which is based on measurements on a 2-inch plug, and run it through the process I'm going to describe here, you end up with this kind of rel perm curve, which is the pseudo curve. But you also have an upscaling of the model itself from a 5-layer model to a single-layer model. And that upscaling, you want to preserve the thickness and the permeability thickness, the permeability times thickness of each layer, that added a cumulative kH. And you want also to preserve the pore volume, which in this case would give a thickness of 31 feet, obviously. And the permeability in the upscaled model would have to be 29.5 millidarcy, and the porosity would be 15 porosity, 15%. First, some elementary theory. Darcys Law states that in a single phase case, when there's only one fluid present, the flow rate is the absolute permeability times the cross-sectional area, the flux surface, multiplied by the pressure drop across the model, divided by the formation volume factor and viscosities of the fluid, and the length of the model. That's Darcys Law. we're going to have to uh, find what that value is for both water and oil. I'm going to explain how to do that later. The relative permeability comes in when we talk about two or more phases, because when there's less than 100% water, then the flow rate of water will typically be somewhat less, and the flow rate of water as a function of the water saturation would be the relative permeability, which also is a function of the water saturations, times the single phase rate if everything else is equal. The pressure drop and everything is the same. Then the relative permeability is simply a proportionality function between the two, or a ratio between the two. And we're going to use that to generate the pseudo curve. That's why we need to find the baseline flow rate, or the single phase flow rate of both water and oil. So the first step is to find what the water baseline is, the single phase case. And we do that by simply modifying the input to the model by setting the relative permeability to water equal to 1, regardless of the water saturation. And you do the same or a similar thing to get the baseline of oil rate by setting the oil relative permeability to 1 for all water saturations. When you've done that, you're ready to run the two-phase case. And then for each time step in that simulation, you calculate the water saturation and the relative permeability to water and the relative permeability to oil. And the way you calculate the average water saturation in the model is by adding up the water initially in place, the volume, plus the injected water volume, minus the produced water volume, times the average formation volume factor divided by the pore volume of the model. That gives you, for every time step you do this, you get the average saturation of water at that time step. Also, you have the flow rate of water at that time step, and you've already found the baseline flow rate, and the ratio of the two would then be the relative permeability to water, the pseudo relative permeability to water. And similarly, you also get the oil rate at that time step when the water saturation is as it is, and you get the relative permeability to oil at that time step by taking the ratio. Typically, in using this model, the first few time steps will be in a transient mode. It will not be a pseudo steady state condition. So you're going to have to ignore the first steps. Okay, I've opened up the ExcSim model here, and I'll show you what it looks like. Here's the cross-section model, where you can see the 5 layers. And here's the permeability variation, and the porosities, and the saturation. It's oil, basically oil filled, with initial water saturation. Now, step 1 is to find the baseline water saturation, and I'm going to do that by going to the PVT and RelPerm tab here's the water-oil rel-perm curve. I'm going to just copy this for later, and I want water to flow as if it was a single phase case. So I want the water saturation to be 1. Not the water saturation. I want the relative permeability of water to be 1. And I want oil not to flow in this case. Now, when we run the simulation, you'll see the water rates be shown here, and the rates will very quickly converge to a constant rate. Let's see, it starts out with 5 and then 4 and 4, 5, 4.56. It's pretty much stabilized right there. So I'm going to stop the simulation. So the baseline water flow rate is 4.56 barrels per day in this tiny model. Now, I'm going to do most of my relative permeability or pseudo rel perm work on this in the material balance page. So I'm going to paste the water baseline value here. That's the reference rate of 100% water, or equivalent to 100% water. And I'm going to do the same. I'm going to change that to 0 and let oil flow at 100% capacity. And here, because I'm injecting water in one end and producing oil in the other, at the other end, the production rate of oil will not converge as convincingly as this, and it'll take a little longer to converge, but it'll be you'll see it's about 0.7906. That's about where it ends up as the baseline case for oil. So I'm going to take that value and just paste it there. Now, the reason that these values are different is because the formation volume factor is different and the viscosity of oil and water are different. Also, I'm going to need because the cumulative oil rates and the cumulative water rates are reported here in millions barrels. I'm going to need to get the pore volume in millions of barrels. And if you go to the solution maps tab, at the very bottom of that page, you see the pore volume for each grid block. And the whole array, the whole range here is, I've named that range pore volume. You can see here in the upper left-hand corner, and you can see it in print when you minimize the window. The names of the ranges pop up here, but the range is pore volume. So I'm going to go here and I'm going to take the sum of the range called pore volume, and I'm going to divide it by 1,000,000 just to get how many millions of barrels the pore volume is. So you can see I've taken the sum of the whole pore volume range and divided by 1,000,000. because I'm going to need that. So now we're ready to, I'm going to put back my my original relative permeability. Let's see. Put it back there. And just delete this. There's the original relative permeability that comes, say, from a core lab, and that's the one I'm going to upscale. It looks like this. These are the relative permeability curves. The blue one here is the water curve. You see that column? And the brownish one is the oil column. And we're going to generate a new set of curves here for the upscaled version. But for now, I'll just run the simulation. And let's see, we can see the water saturation here near the injectors. You can see water breaking through or shooting through the high permeability layers first, and it will eventually it will reach the producer at the other end, and the water cut will increase when that happens. So here I've got the oil rate, and I've got the water cut there, and I've got the 3D viewer here where you can see the advancing water for every time step. So now you're actually looking at an accelerated simulation where you can see the water shooting through and the water cut climbing, as well as the oil rate declining. And I'll just let you sit and watch it until the simulation is over. Okay, the simulation is completed, so let's go and generate the pseudo curves. In this column, I want the water saturation. Here, I'll put the water relative permeability and the oil relative permeability. Oil relative to water in a water mixture. To get the initial water saturation at each time step, I'm going to take the water initially in place, which is that value here, and I'm going to add the cumulative water injection, which is that value, and I'm going to subtract the cumulative water production, which is that value. Now, I'm going to multiply that with the formation volume factor of water, which I find there, and I'm going to divide that with the pore volume in millions of barrels, which is there. So you can see that initially the water saturation is 10%, which that's the initial water saturation. Next, we're going to get the relative permeability of water by taking the water rate at that time step, which is the water rate is here, and divide it by the baseline water rate, which is that water rate there. It's practically zero, as it should. And similarly, the oil rate, or the oil relative permeability, would be the oil rate, which I find here, divided by the oil baseline rate, which is there. And I'll just copy those formulas all the way down for every time step. To there. So this is, if I plot it, this is what we get directly. You get a pseudo rel perm curve for oil, for water, and for oil here. Now, initially you have that transient behavior, which we're going to have to ignore. We'll just cut it off at the lowest value here, which is about, let's see, from that point on, that gives a, well, let's see, maybe that one's lower. That's the lowest point, and that would be the starting point. And what you see here is that the oil rate starts at, the relative permeability starts at 80%, which is the same, if you go here, it's the same as the initial rel perm, 80%. But then as the model gets filled with more and more water, and water is less viscous than oil, the mobility increases of the system increases. So water, the water rate will actually increase until it breaks through in the first high permeability layer, and then that high permeability layer will produce only water, so the oil rate drops, and so on. You get this shape, and it will continue. You can extrapolate this curve to about 0.5 at 80% water, and that one to 0 at 80% water. Because again, if you go to the original one, you'll see at 80% water saturation, the rel perm to water is 50%, and the rel perm to oil is 0. So you can adjust the rel perm by extrapolating, or by adding at the very bottom a water saturation of 80, a rel perm of 0.5, and a rel perm to oil of 0. So just go add that last point to the curve. And it kind of completes it. So you can take this part of the curve, actually you can say that is 10%, and that is 0, and that is 0.8. For example. And there's a 0.10, 0, and 0.8. You can take that part of the table and copy and paste it into the real perm curve here and get a very long real perm curve. Or you can just pick out a handful of points that describe the main characteristics of the real perm and end up maybe with 10 or 15 points to describe the whole curve. And that's pretty much it. That's how we basically generate pseudo real perm curves in ExcSim. Just be aware that when you copy this or copy a handful of points from this over to the real perm curve table, let's see, over here, you also have to generate capillary pressure curves for each of the saturations you choose. And there are several ways of doing that. You can either keep these and just replace each of the lines here and keep those as they are and keep the water saturation as they are. Just look up what say the 30% water saturation, what is the real perm. There, if you go to 30, there's 30.7. Just use those values and leave the capillary pressure as it is, or you can change it. But I think I've gone through the main methodology, and you should be able to generate your own pseudo curves, and you should now be able to emulate a 3D model, layered model, in ExcSim by means of pseudo real perm curves. So thanks for watching, and we'll talk to you next time. Bye bye.